create this workshop, and I would like to thank for this opportunity and for organizers, especially for the webinar. So I'm going to talk about the title is here, is Fidelities in the spin-boson model. So the work is based on this couple of papers. Here are the references. And so let me start with a very few words about the general picture. So in principle, when we have, I will talk about the quantum field theories, and the theories which contain the spectrum that exists with the massless excitation, gapless excitation, right? And in these situations, if you do any perturbation theory, let's say, then you will observe immediately observe infrared divergence, and the problem with infrared divergence is a central issue in such a theories. And historically, the first example was a problem with the soft photons in quantum electrodynamics, but in condensed matter physics, it was people started to think about after the final works of Anderson about the orthogonality catastrophe. And so I'm going to discuss actually kind of the simplest possible situation, simple possible models. I'm going to talk about the 1+1, let's say, two-dimensional conformal field theory, let's say, and by the theory with certain boundary interactions. Let's start with the conformal boundary to see the problem. Just remind you how it works. So, and I would prefer to talk about in the Euclidean pictures, right? So the space, the space would be, we start in the conformal, we start the theory with the boundary, so the space coordinate, it's a ray from minus infinities, let's say to 0, Euclidean time, so we have, basically it can be understood as certain statistical systems with the critical bulk. Since we have a boundary, we also impose the boundary conditions. Let's start with the conformal boundary, labeled alpha beta. And for given, once you choose the boundary conditions, right, and they consider the Hamiltonian pictures with the space along the half-infinite line, then we can, we can think about the vacuum corresponding to the given boundary conditions, and the statement of the famous statement, then the vacuums corresponding different conformal boundary conditions actually are orthogonal. Well, to be more precise, the overlap of the vacuums corresponding to different conformal boundary conditions are suppressed by the size of the overall size of the system, space size of the system, this is L, with a certain power, and to get this formula, so there is large L estimate, it's very easy. You just use the advantage of conformal symmetry and map the half-infinite systems to the strips by logarithmic map. You need to do the logarithmic map, get the theory in the strip, and with the different, again, with the different conformal boundary conditions, and then clearly at the time now, it's suppose the time it's along it's coordinate along the strips, then the whole time is logarithm L, and then immediately see how this can derive this formula. Again, so this is a...
Okay, I guess the width enter in A alpha beta, right?
So
I mean, there is the width also the strip.
Width is pi.
Ah, okay, so it's...
Well, you logarithmic map it's pi. Right? This angle, the width corresponds to this angle, to the whole vector. So what's important, of course, we can do this at any size. All right. So this is a famous, this is manifestation of orthogonality catastrophe, and then in principle we can say that in slightly different manner, because to avoid any divergent quantities when infrared regularized quantity, we actually can consider the statistical system is the system is a slightly more sophisticated, more complicated, with the boundary which involve split on the three parts, right? Suppose we impose the half-infinite bound on the two rays, right? I'll impose the conformal boundary condition alpha, and only on the segment, a finite segment of length y, we impose the boundary condition beta. Then we consider the statistical partition functions, normalize it somehow, right? Divided by partition function with homogeneous boundary. And these quantities, this ratio can be interpreted as an expectation and the two-point functions of so-called boundary condition changing operators. This is notion introduced by Cardi. So that this can be interpreted as the two-point functions of the boundary condition changing operators, and because of the scale invariance, clearly this quantity should be just a power law with a certain exponent. And now, and a certain coefficient here, I introduce also certain coefficients. Now you see that in principle you can try to calculate these two-point functions slightly different manner, just introducing the complete set of statements between the operators. And for example, if you introduce the vacuum state first with the vacuum here, vacuum contribution, but as I said, this overlap can be now interpreted as a one-point functions of the boundary changing operators. And as we saw, this contribution actually vanished as L goes to 0. L goes to infinity when the size goes to infinity. And the same story happened not just for vacuum, but any conformal descendant, any states. Well, using the language of quantum mechanics, the state with the soft photons will be actually contribute nothing because they are suppressed by the power by the total contributions. Then when you sum over the all contribution contribute of all conformal descendant, there you get some finite answer. So this is basically the mechanism. And here we also with the orthogonality exponents delta here, you see some constant here, right? And of course this constant, it's just constant for conformal field theories, and it depends on how you normalize it. It essentially depends on normalization. So the normalization, there's some freedom. Generally speaking, it's not universal, but because of the you need to impose certain normalization conditions, and in many cases you can just set it to be 1, so it's not particularly interesting, this constant for conformal theory. However, once you the same story, now the situation becomes much more interesting once you consider the theory, conformal field theory, but with the boundary conditions, but not conformal. In this situation, you can understand as a boundary flows. So the boundary conditions, the boundary condition may depend on the set of general dimensional parameters, right? And depending on the scale you're interested in. If you're interested for very large scales, then it looks like in the conformal field theory with certain conformal boundary. So, and you start in this conformal boundary condition can be understood as the flow from ultraviolet conformal boundary condition to the infrared conformal boundary. So let's now repeat the same construction as for conformal case. So we consider the following systems with the homogeneous boundary. Now mu1 and mu2 are labeled the different set of parameters of the space of which describe the interaction of the boundary. And again, we can introduce the partition function for such a systems, normalize it, partition functions, and now it depends on the distance here, y, and for non-conformal boundary, this function, of course, because now we don't have a conformal symmetry, this function is rather complicated, but we still can address the questions about the large, let's say, y asymptotics. And from very general argument, you can expect that the asymptotics now has this form. It has additional exponential suppressions where delta epsilon 2, it's a difference of ground state energies for different boundary conditions. Now it's not 0. So we have, strictly speaking, we have a gap here. But we still have some power law. Some power law with defined by the certain critical exponent and the amplitude 81. And again, we can interpret this amplitude as the kind of part of overlap. So the overlap, still the vacuums corresponding to different boundary condition would vanished as L goes to infinity, but still we have the certain coefficient here. And now these coefficients depend on the parameters of the systems. In principle, it's a certain scaling function, so the parameters. And so this, which define this overlap. Okay, and I would, well, using the model is conventional terminology, I call it as a fidelity, ground state fidelity. So the overlaps of the vacuums correspond different parameters of the interacting limit. Okay, and the questions, what can we say about this? Of course, the first question should be what are the exponent here, and what are the fidelities, what are the amplitude.
Sorry, you call vacuum omega 1, omega 2, you call vacuum, but it's not really.
It's really vacuums. It's vacuum.
No, it's a boundary state.
I'm doing the theories. I'm doing this here in the channel where my space is half infinite. I import the boundary conditions here. Right. So I'm doing the theory. So this is my space, and this is my boundary. Suppose this is my space, and I'm quantizing the theory on this, and the boundary labeled by the parameters, set of parameter mu. And I write the Hamiltonian. So the Hamiltonian acts on this
what
space.
they usually call the vacuum in Virasol, which is.
I think it's what we usually call in just the quantum mechanics. Because this is just usual picture. It's a state with the minimum energy. The state corresponds with minimum energy Hamiltonian defined on half infinite line with a given boundary condition.
And it's not normalizable state.
Well,
so it's not part of the Hilbert space.
Why?
It's not normalizable.
Well, if you particularly worry about this, let's put the boundary also here. Put some simple conformal boundary conditions. So then it would be complete.
Okay.
But this dependence actually. Of course, you can regularize. You are right, and you can principle you need to put it in the steep, right? And but here you can put this as trivial boundary conditions and not have all dependence of this part.
It's a matter of terminology.
That's matter. But anyway, we are talking. Of course, we are interested in the universal part. We're talking about this amplitude which depend on the scaling functions. All right, and what I'm going to discuss actually in my talk, a model, it's a spin-boson model. It's one of the simplest boundary theories. So it can be formulated the following way. As a bulk, right, at the half infinite line here, we just put on this line the free boson field. Just a Gaussian field, massless Gaussian field. So the Hamiltonian, the Hamiltonian is this one. This is canonical momenta, canonical. This is canonical coordinate phi, right? Canonical momenta with the canonical commutation relations. So it's a Gaussian field, massless. No, bulk is free. We start with the theory which has three boundary conditions here. Neumann boundary condition. The derivative, normal derivative vanished. It's a conformal boundary conditions. But also we include a certain interaction in the theory by adding the additional degrees of freedom at the boundary. So we have a spin. Let's say the spin acts in the two-dimensional space, right? And we introduce interactions. We couple the spin with the boundary values of canonical momenta by here. It's a boundary values. B means boundary values. Also, we include a certain coupling here, G and H, the parameters of parameters, the couplings. And after that, we have a vacuums, right? We have a vacuums, which is labeled, which is characterized by two couplings, G and H. And for different values of G and H, we have a overlap. the overlap, they are vanished, as I said, it's vanished with the certain power law again, and here we have fidelities will depend on the certain on the couplings, and that questions about how to calculate. And this model actually is a kind of some basic model in quantum, dissipative quantum mechanics actually can be formulated. It's equivalent to the using the, you can fermionize the bosons here, and the boson can be formulated as a so-called anisotropic quantum model, right?
These parameters are genuine parameters.
Yeah,
they
this
do not
is
renormalize. I mean, I
yeah,
can assign
you
value
start
one
with-
after remain one after.
Yeah, these parameters is bare parameters, right? And I will the normalized parameter I will use normalized parameter, the quantum temperature.
But it will be the bare.
This is better. This is just how it appears in the. Of course, they need renormalization. The ultraviolet divergences here need to be renormalized. All right, and well, and first I want it's very simple theory, conformal field theory. First, I would like just remind you how so you see the space, the operators here acts in the tensor product of the space of Hilbert space of the free boson H, curve H, it's a Hilbert space of the free bosons, and C2 it's a Hilbert space of the spin. Okay, so this is, let me just remind you how how the free boson Hilbert space can be constructed explicitly. So we have a quadratic Hamiltonian, and you can diagonalize it by just a Fourier transform. This is the transformations, introduce the creation integration operator satisfying these conditions. And after this linear transform, the Hamiltonian take this form of the set of independent harmonic oscillators. Then you build a vacuum, just constructing the Fock space. So you start with the sort of with the highest vector, the Fock's P vacuum, we call it, which is neglected by the creation annihilation operator pk with k positive, and create whole space by acting on creation operator with negative k, and also you have zero modes here, b0. Let's correspond k equal to 0, and then B0 commute with Hamiltonian. So in principle, this Hamiltonian has a huge degeneracy, and it acts irreducibly in each Fock space, but the energy, each state has the same energy. And so in other words, the vacuums for what we are interested in the vacuum for the particular boundary condition, it's a linear combination, certain linear combination of the fact vacuums, of the P vacuums. How to construct this, how it looks like? Well, just well, again, it's I will use, as I said, I will use the Euclidean picture. I make the weak rotations here, use the variables x and y. Here's my world sheet. And then the vacuum, well, in principle, the vacuum for the Newman boundary condition can be described by the direct integrals with just a Riemann measure of you sum all Fock spaces with the same weight, right? Another way to formulate the property that this is the vacuum of the theory with the free boundary conditions. But another way actually that's not particularly convenient for us. Another way to set that characteristic property of the vacuum can be formulated following. That is, once you apply the vertex operators, exponent, and send y goes to infinity, then satisfy these conditions. More or less, this condition is easy to understand, because in classical level, what you are doing, you're solving just Laplace equations, right, with the Newman boundary conditions, right? And it's really the solutions has some freedom. You can always add the constant, right, which is not a function of the solution. And usually we set this constant infinity to be 0, right, potential. And the more or less, that would be the analog of the condition. So I send here the infinity from the boundary side. The condition is more or less at the peak, somehow it's disappeared with infinity. But it is important. These conditions is kind of important, would be important for us. And the whole Hilbert space, you start with this vacuum and then create the Hilbert space by action of the creation operator with the positive k, with the negative. And what's really important for us, the exponential fields, exponential operator acts invariantly on H. So if you, this will not, once you, this operator exponent acts in the Hilbert space of the theory with free boundary conditions. So this is our Hilbert space. And another important, well, simple but important fact, that the theory with Newman boundary conditions, so this is basically the Laplace equations, with Newman boundary conditions, you can solve it, right? You can, equational motion can be expressed, solved, and the solution can be expressed with the sum of galomorphic and galomorphic paths. And actually, they're the same function. Phi small, it's the same function because of these boundary conditions. And you can formulate the theory, a meaningful theory of chiral Bose field on unfolded half-infinite line, right? So you just this transformation just unfold the half-infinite to the just a whole space, and the field y lives on the space and satisfy very simple equations of motion. This time evolution, Euclidean time evolution, just a condition for the homomorphicity for this function phi. Hamiltonian is simple, but the price we pay for since it's not it's a chiral field, so the commutational relation is not local anymore. Commutational relations involves the step functions, which is not local commutation relation. Okay, and first I want to explain that this problem of calculation of fidelity, and this problem is it's related to the quantizations of quantization of auxiliary linear problem for KDV theories, or quantizations of nonlinear of Schrödinger, just using Schrödinger equations. Why? Let's consider the limit when the coupling, here at the Hamiltonian, here at the coupling, suppose the coupling is G. It goes to 0, it's a big coupling regime. In this case, we can understand the dynamics, the physics as a interpret as the motions of the quantum spin in the presence of classical background. Certain classical background, we in the classical limit we can think now about this operator as just a classical field, which is given for us. We satisfy the certain asymptotic conditions. T asymptotic conditions that's dictated by the term, by the magnetic fields, well, the term which is coupled to the sigma 3. So we have a certain classical field, and which coupled to the quantum spin. So what we have is Schrödinger, just a Schrödinger equation. And this is this is a second order. This is first order matrix differential equations. 2 by 2 matrices here, right? And well, the problem discussed probably most textbook in quantum mechanics. We have a field, constant field, along the x directions, and also the time-dependent component, which is along the three z directions, and what happened with the spin, right? And what we, as usual, what we start solving this problem, we need to construct the time evolution matrix, right? It's a p-ordered exponent. I write it this. I write in this way. It will be convenient for me because I'm preparing for quantization. So I will write in this following form the time evolution matrix. And then the question I would like to address here: suppose we at moment t equals 0, we start with the state which is when the spin is up, right? Suppose we start with the magnetic field, with the field H, right? Which is, let's say, positive, right? So that would be the ground state. Suppose H is small, but positive, it may be small, but this state would be would be the vacuum for the non-interacting systems. And then we apply the time evolutions and see what happened with the states, and assuming that T0, so T is a certain reference point, we can set this, finally we can set this T equals 0, right? It's absolutely irrelevant. But what's important, we consider the limit when T0 goes to minus infinity. So initially, the moment and infinitely passed, we consider that the infinite past, the spin was enough conditions. Then it's straightforward, since it's just a second order, just a usual differential equation, straightforward to show that as t0 goes to minus infinity, this time evolution involves two terms, which is both oscillate, right, with a certain phase, and the coefficient here, k, express it written in the certain combination, which doesn't depend on t0, of course, because we are talking about t0 minus infinity, but they depend on t, and this function is actually the certain solutions of you can write it. You can solutions of the Schrödinger-like equations, right? Second order differential equation. As usual, you have a matrix, a first order differential equation. You can transform it to the second order differential equations, but and this in this case it would be just Schrödinger equations. This J is like J squared with the Rolls energy, and U is a potential. Right? And this transforms, sometimes it's called Muir transform, from the potential from the phi to mu. Anyway, so what we need to do, we take these equations and consider the solution satisfy certain asymptotic conditions when t goes to minus infinity. It behaves like a plane wave, right? Where k is g squared plus h squared, because the u, and this is a behavior, asymptotical behavior, and then we need to solve this equation, this asymptotic condition. This condition defines the unique solutions uniquely, and then these functions appear in the limit. It's a so-called just solution. This function is called just solution. We have two equations in fact, different potentials. All right. Anyway, so now we have this formula, and now we take the limit, but there's no limit. Right, the two terms oscillate, and but in principle, the first the oscillations of the we can easily make the suppress this oscillation, because assuming then as a norm that is usual.
How this parameter k emerges there?
K it's a g squared, and it's asymptotic u. It's controlled by h squared, right? So this is a and the potential, what's important really, I should emphasize, that this potential is not fast decaying. U decays to minus h squared when t goes to minus infinity. This is most important for us, because it makes the problem much more complicated. Okay. I'm sorry, probably this is wrong. It should be k plus h. Okay, anyway, so the first exponent, we can easily understand avoid this oscillation if you assume that the interaction adiabatically switch off as t0 goes to 0. So suppose the coupling G, the G here is adiabatically switch off at t0 goes to 0. Then from this formula you see that k became h, right? And the k minus h turned to be 0. Right? So by assuming the adiabatical switch interaction, actually this oscillation will disappear. So no problem with this. But this should be plus. I'm sorry, this k plus h. So these terms will be still oscillate, and we need to suppress this. If you want to suppress it, do some tricks. And the tricks is simple, right? Just assume that now that t0 actually complex, and we adjust the imaginary part of t0 in such a way that this oscillation became the exponential suppressions, and this is usual. So what we call the weak rotations, right? The quantum field theory, yeah, right? So that is from the point of view, in quantum field theory point of view, this is rather natural assumptions, and but once you do this limit along this certain imaginary directions, then this term disappeared, and you finally end up with a certain finite answer, and which I write in this way. I said in this formula, I said t equals 0, and you get some state, right? You get some state which is a given sum of this up down spin with a certain coefficients, and this is a value of these coefficients more up to these factors. It's a value of the just solutions at t equals 0, with the reference point t equals 0. Right? So that is gives you the answer for the behavior of this spin. Okay, and so they have just functions, and they satisfy. Of course, they have probability, the probability, the total, the probability to find the spin both in up and down position equal to 1. So then we have these conditions. These coefficients satisfy these conditions. So in other words, you see that the classical limit, the problem reducing to the Schrödinger equations, but now we would like to you remember that we start with the classical field, and now we would like to quantize this, make the fields phi, which is appears in Schrödinger equation, actually be the operator acting in the certain Gilbert space. And we would like to now the question how to quantize what can we say about this now it will be our just function became the operators, and the x in the certain Gilbert space, and what can we say about this? So the problem actually is close to the this problem was discussed in my old work long time ago for in the context of Sine-Gordon model. And the similar actually the ideas behind this is very similar to the idea of subvertex operators approach, especially developed by Jimbo and Miller for the latest systems. But actually the new path, so the problem of this problem which I'm going to, what's interesting now for me, that we are considered the case of Schrödinger equation with this, the potential now is not fast decaying, it decays to a certain constant. This is so-called the case of the finite density case. You know, in nonlinear Schrödinger equation, the simulus equation called finite density case. And this is much more complicated. We know from the classical inverse scattering method that in this situation they should expect much more complicated analytical structure than the fast decaying solution. So that and this is why the problem is not trivial. Okay, and first we need to get some idea what are the operators. So now the just operators, just functions, the operators. So how they act. So what some idea about these operators. And probably perhaps the simplest way to understand it use the so-called mean field approximations, which based on in principle the idea is to start with the simplified Hamiltonians, this kind of approximation, which is in spirit of mean field. We have interaction with the spin, and let's just replace the spin degrees, just the average value of the spin, the magnetizations, right? If you replace certain number m, then you immediately the Hamiltonian split into two non-interacting Hamiltonian. This is part which acts in the Gilbert space of the free boson, and this is a matrix, 2 by 2 matrix. So now you diagonalize them separately, and you diagonalize first the Hamiltonian H2, find the ground state, and find the magnetizations, so which is just a derivative of, with respect to fields, and you substitute these equations, use this, and then they do this diagonalization, right? It's mean field, well, spirit of mean field. And what the Hamiltonians now is very simple, and you can immediately write the time evolution operator, integrate it. And this is explicit expressions for the time evolution operators, and you apply it to the vacuum. These operators clearly, what I should emphasize, that it's combinations. This X exponent operator, and each exponent acts invariantly in the Hilbert space of the free theory. So, so the vacuum of interacting theory can be obtained through the sending the limit, sending t0 to actually minus infinity, right? So this is a vacuum state for the Hamiltonian H1 plus H2, so the matrix part, and the tensor to the vacuum, the vacuum for non-interacting theories, and apply the. So this is a modulus interaction, the vacuum interaction picture. Right? So the most non-trivial part here is how to understand this limit, how to send t0 to minus. And again, again we do this by doing the weak rotations, the imaginary time, this weak rotation, and remember the characteristic property of the vacuum of the free boundary, of the state with the vacuum state for the system with the free boundary condition, that this limit actually exists and gives the vacuum. And this is what's important. Otherwise, you know, this is why. And finally, you end up with the expression for for the ket and bra vacuums, which involve the operator T plus T minus, the kind of mean field approximation for the just functions, and this is just exponential fields. And they are, of course, the Hermitian conjugate. Of course, it's what's important, if you take a look on this formula, you see that these operators acts indeed, this is exponent, that it acts indeed in the Hilbert space of the free boson field. But what's important, because the Hilbert space, remember that the Hilbert space H is a direct sum of the Fock spaces, and the exponent acts between the Fock spaces with different value of 0 mod p, and is shifted on the value of the magnetic moment, which depend on H. Right? And the conjugated operators. All right, and now you can immediately see, so suppose in the vacuum, you see that the vacuum of the, we can interaction theory, you can interpret it as a coherent Glauber state on infinite system, non-interacting harmonic oscillators, so it's just
It was my point.
yes. Yes.
Okay.
Okay, and so the overlap now, it's a the overlap is just expectation values of exponential operators, which is m1 minus m2, right, which correspond to vacuum 1 and 2. This is exponentials. And of course, 1 point functions, well, if you insert the 1 point here, this 1 point is 0, strictly speaking, and it's suppressed by the size of the systems L with the certain exponent, and this exponent is very easy to
Yes. You fix the phase, right? So at the infinity. So is there any choice of different phase, for example? Can you is there freedom actually in fixing this phase? Which remember in boundary conditions when you say
what phrase? This one?
no, when e to the I and phi acting on vacuum was equal to vacuum and t.
Yeah, what phrase?
So in the beginning of your talk, you fix the boundary conditions of infinity.
Yes, so for example, I put the free boundary condition of infinity here.
But this fixes the phase as well, right?
Yeah,
So
yeah, there's some ambiguity in the phase.
no, but then if this phase can also enter your overlapping principle, right? If you choose a different phase, for example, I don't know how much freedom you have in fixing this phase.
Well, this is all these phases is kind of separate, it is split in the factors, and the contribution which come from this boundary will be, I just focus on the contribution from the boundary from which the
I remember when you talked about Laplace equation.
yes.
Yes, so you said that there is this constant, and also I fix this constant. You said
Yes, you can put it any constant. It's the phase itself, the constant phase itself, it's a matter of.
So you're saying that this phase doesn't affect you.
I'm interested in only what happened in this. The value, the particular value of this phase, of course, it's a matter of normalization. Well, but it's a kind of so of course I'm interested in only the quantities, the kind of universal quantity. I can avoid all this stuff. We just formulate it in such a way. There is no questions about such equations.
Sergei,
Yes.
can I see this system as kind of bosonic condo?
It's not a bosonic. Actually, it's equivalent to the anisotropic quantum model. You can fermentize it, and it's identical.
Yeah. Another question is, imagine that the tier in the bulk is interacting conformal, not the free one. You have a notion of coherent states in interacting tier?
No, I don't know. No, not in general. I don't know how to. It's kind of simplest. I can imagine. No. The answer is no. I don't know in general how to. Okay, so this is expectation values. Again, we do this logarithmic trick and find this the exponent clearly is just dimensions. It's dimensions of this word boundary vertex. And here is the coupling J and the magnetization. So this is and this is a result for mean field result. But remarkably, it's turned out that if you now identify M as the expectation value of sigma 3 for the interacting theory, that this formula seems to be correct, exact. And this is, I don't know, probably for the experts, it's condensed matter. It's a trivial fact, but for me, I still don't know how to prove it. Because it can be supported by the mean field analysis, then the perturbation, you can do the perturbation theorem in G and the D see the same. Also in Toulouse limit, when all this can be described in terms of free fermions, it's a coupling J for 1/2. conformal perturbation, and also numerics, probably the most convincing fact that the numerical populations actually shows the exponent actually is correct. For any j. So I will accept it as exact. And now what's the fidelities? The fidelities is, suppose we do in these systems, we put the Gaussian system here, we have a system with this bulk G1, H1, and G2, and consider the two-point function. Now there is no any problem. This partition function is well defined. You can do this. Suppose you put the statistical system with the critical bulk, and then define this ratio, and of course the contributions of the boundary import here is actually cancelled because of the boundary here for the homogeneous. You divide it by Z11, and the all dependence on the boundary at minus infinity actually. So this ratio, each of the function of course diverge but the ratio. Now this is a functions, and these functions once you introduce, you can actually consider the situation when you in this point when the different bounds meet each other, you introduce a certain operators. For example, you can put identity operator for sigma 3, right? And and that would be the two-point functions. And since ultraviolet behavior of these two-point functions, when y goes to 0, it's very simple. You normalize it. You can easily you fix the ultraviolet behavior when y shrinks to 0, because in this case it's kind of theory is kind of free, no interaction. To forget about interaction, so the spin is decoupled. So the normalization is clear, so that I write this explicit normalizations of this function for short distances. But the questions for the large distances, what happens once you normalize it, no any ambiguity, so it's well-defined functions. And what happened when y goes to plus infinity? And again, we expect that it has a behavior with a certain amplitude, fidelities, all right? And this fidelity depends on operator, and so it depends. Well, I will use the operator O plus minus, which is a linear combination 1 sigma 3. It's just convenient for convenience. And different fidelities for different operators related is really linear relations. I will prefer to talk about the fidelities of this operator.
Did you discuss yet this issue of renormalization of J and?
Okay, here is. Okay, so but again, as I said, this is actually this is I'm talking about the scaling functions, which is as functions of certain. In general, we have not together with the infrared divergence, we have ultraviolet divergence. Here we should include, in general, well, for the bare matrix element, we expect that you have an infrared divergence, but also ultraviolet, which is controlled by the parameter ultraviolet cutoff epsilon, with a certain dimensions, which is dictated by these operators, dimensions, scaling dimensions of these operators, and epsilon. And actually, we after cancellation of the ultraviolet divergence, we can do this by introducing, by absorbing all divergence in the bare couplings and introducing the physical parameters, certain combinations. If you now send epsilon to 0 and simultaneously send g to infinity, right? In such a way that these parameters keep fixed, then we have a certain limit, which is called a scaling limit, and this parameter actually set the scale, energy scale, physical energy scale, with in context of quantum model, it's called quantum temperature. So this is a formula for this, and in other words, so the fidelity would be the functions of the magnetizations, and actually the ratio. Well, we can in principle there are 4 dimensional parameters, but only 2 dimensionless, and we can use it in magnetizations M1, M2, and also the ratio of the quantum temperatures, logarithm. We prefer to talk about alpha is logarithm of the ratio. So in other words, I also include certain factor dimensional, because alpha is certainly is a dimensional, right? It's multiplied by, it has a dimension, so it has certain dimensions. But I extract these dimensions and introduce dimensionless amplitude, which is a function of 3-dimensional variables, M1, M2, and alpha, and that is my amplitude. And in the approximation, mean field approximation, the amplitude is already calculated. Actually, very simple to calculate. It doesn't depend on alpha. It doesn't depend on the ratio of the complex scales. It depends on quantization. But then you can proceed with the perturbation theory, and you get rather well, not particular, not simple, not well. It's not still the result. You see, the delta here is dependent on alpha. It's delta. So it's rather the calculation is not particularly simple here. So in principle, you can do the order by order these calculations, right? You calculate the fidelity in the power series of G. But of course, we want to be interested in the quantizing the systems. Kind of, we expect that the system actually integrable, and what can we say about exact results? So again, and so in principle, here's the idea. So we remember that in the classical mechanics, starting with the classical pictures, the evolution operators, this matrix time evolution operators had this form. And now I would like to quantize this form. I would like now think about phi as a quantum operators, as a glomorphic field. So, and the complete, I just, actually, this formula just shows the formula for the classical version, but in Euclidean time, right? Why it's Euclidean? And also include the mu in my coupling, it's would be renormalized coupling. And I'm going to do this coupling. I assume that this coupling is adiabatically switched at infinity, right? So at minus infinity, the coupling becomes 0, and then have a finite value, and then switch again. Right? This is it. And this size give me some infrared cut-off scale. So this is me. And once we impose this, assume that the coupling is adiabatically switched, in principle, we can take the limit, then y2 set to 0 and 1 goes to infinity, because actually the interactions is restricted to the domain. So this object is well defined once you assume the regularizations and parameterization. But of course, the main questions now, what happens when we send L goes to infinity? When this, and this limit is highly non-trivial, it's not trivial to do. But anyway, we expect that the limit somehow exists, somehow. And in the result, when you send L goes to infinity, apply the evolution operator, because some constant diversion, but finally you get the vacuum interaction theories here. Okay, and I don't know how to do this limit, and the best we can do is just postulate that existence, and just try to guess the property of the state. And having experience with the mean field and the classical limit, we expect that the vacuum has these structures. We have an up and down component, and the operator T plus and T minus, certain operators, Q plus and Q minus, certain operator, which acts in the Hilbert space of the free boson field. And again, we just use the experience from the mean field, expect this operator acts exactly like a mean field operator with M, where M is magnetizations in exact magnetization, which we know from the solutions of the anisotropic lambda model. This is a formula for magnetization in terms of the renormalized coupling. Lambda, this is a ratio of coupling of dimensional ratio. And you see that, and this is I should emphasize this is very non-trivial assumptions, because if you start naively expand the exponent in this series, right, you see that you have an exponent. You take the p-ordered exponent, right? This is expand in terms of mu, and formally send y to infinity. And what you get the expression like this. And these operators shift p by 1/2, not by m. Because it's only for h equal to infinity, you get the 1/2. Magnetization equal to 1. So that is x, and but the series actually is infrared diverge. And once you the conjecture, once you sum over the all divergences, that the effective result would be the operator action in this case. In particular, if you consider if you h equal to 0, then it will not shift p at all. So it is very confusing, right? This is a strong, very strong assumption. Anyway, this is assumptions, and then we have a T and Q operators, and then the combination T and Q, it's more or less a T, it's evolution time from minus infinity to this point, and this is T, and this is Q, right? And the product of them, it's a kind of insertion. It's a change boundary analog of boundary condition change operation for the boundary flow, right? This operator play the roles of change the boundary, because the boundary here is controlled by one set parameter, this is another set, and the mu is the h are different sets. So it's this bilinear combination is kind of analog of the boundary condition change operators. And our universal amplitude is just expectation values, vacuum expectation value. This operate x in the space of the free boundary conditions. So it's x between p and Fock spaces. This is vacuums. And but we expect that just operate x invariantly in this Hilbert space, and actually all the dependence actually only come from the delta symbols. There is no dependence on each amplitude actually doesn't depend. The amplitude, universal amplitude, which is fidelities, right? Fidelities doesn't depend on the choice of fields. Similar as it was for infield. Okay, and then this is a first assumption, of course, and then we can just guess the property of this operator using the global symmetry. There's some certain elementary symmetries of the problem, like a T invariance, and the T invariance, it's anti-unitary operators, and imposes certain restrictions for the how certain symmetry relations for the amplitude. This is a relation. Also the hermeticity, of course, here, and it also imposes the relation for the amplitude. Important property is the C invariance. In principle, the Hamiltonian invariant with respect, if you replace phi to minus phi and also flip the sign to sigma spin, that is the symmetry, and this symmetry is not spontaneously broken. It's not broken. It means that actually the point h equals 0 is not singular. So you can smoothly continue the operator. Actually, the nose doesn't have a singularity h equals 0, and you can continue to analytical, continue to the point a negative magnetic field, which is unusual, right? Usually you have the symmetry is spontaneously broken. But here, in this situation, the symmetry is not broken, and you can define the C operators here, and also conditions, conditions for the amplitude. And probably the most important fact, which is kind of the dynamical equations in this picture, is this Lorentz invariance. And the formula which we expect here, that applying the Lorentz transformation. What is the Lorentz transformation? It's a rotation, right? You rotate on the angled side. Rotate on the angled side, and in the Euclidean plane. Of course, it's a Euclidean plane. So under the action of the Lorentz boost, you can compensate it by rotations of the field h and parameters, the angle phi. How to show this? Well, it's kind of again, not prove it, but we have some heuristic argument. So we start with the formal expression like this and apply the Lorentz boost. This is insertion of operator in the center, right? Of course, we rotate about this point, so this operator will not affect it. But these operators, since they're here, they actually rotate. But remember, this is galomorphic field. Once you rotate, you just calculate the value on the certain different on the ray which is obtained by rotations of this ray. But this is galomorphic field. An integral here involves the integrals over the galomorphic field. And for this reason, assuming that there is no contribution from the infinity, you can return it back. The contour of integration, because it's galomorphic. And but of course this field is have a certain spin. They are not. They have the chiral has a certain dimensions, and after the rotation, actually there's some certain phase appeared, which can be absorbed by the coupling. And this is why this coupling, and this is my minus j. J is a spin of the field. nullify, since you rotate Z, you also should rotate H. And this is how this formula is appeared. And this is it's kind of most important, it's dynamical equations. And then, so you have a picture, so you can show that from using this, you take, for example, if you start with a T operator that from responding to this side, rotate an angle 180 degrees, you get the operator Q. So the rotation on the angle 180 degrees, you can start from operator Q plus, you get operator Q minus. In other words, you can work only with the operators T. Using this Lorentz invariance, the advantage of the Lorentz symmetries is that everything can be expressed only in terms of operator T. You can forget about it. And finally, so in other words, for example, the amplitude, the amplitude, which is Fidelities, we are interested for, can be expressed in analytical continuation. It can be related to the two-point functions of the T operators, of the which is just operators T plus and minus, and just doing the analytical continuation and the complex value of magnetic moment. So this is a picture. So this is a relation which is important. Okay, also finally we have a relation like this, which is an analog quantum version of the classical relation of conservation of probability. You have some quadratic relations. Okay, and okay, so you see that a certain type of relations, and in general, I still do not know how to do the general case when magnetic fields is arbitrary, but some interesting prediction can be done in the case when the field H1 equal to H2. In other words, we just here H1, H and H remain the same, and only the quantum coupling, only J would be different. In this case, if H1 equal to H2, the fidelity depends only on two variables, M2 and M1, because alpha actually is not independent, they satisfy these conditions, remember. So when only two parameters, only two independent quantities. Okay, and so as I said, the fidelities relate to point, analytic continuation to point function of the just operators. In general, we can consider more general object. It's a correlation function of many T operators, not just one, a few of them sorted, and they introduce the function of this type. And in principle, it's better to think about the problem of population, so not just a two-point function, but endpoint functions. And the idea, in principle, the following is more or less follow the ideas from factor bootstrapping usual. So we have operators, and now, if you know the commutation relations, right, you can translate these commutation relations of the operators in the set of functional equations and then try to solve it. So the question is, what would be the commutation relations for the just operators? And you can at least guess them using the following arguments. So you start again, we start with the finite, the evolution operators from the finite, not just infinite, because the just function is it's a kind of transform, it's a monodromy matrix from minus infinity to 0, but we start with the finite monodromy matrix, and now it's possible to show rigorously actually that it satisfies the Young-Baxter type relations with the 6 vertex matrices here. These relations should be familiar to most of you. And then the major questions is what happens when we send to infinity. And the idea is, well, again, it's as I said, the limit, the limit is very difficult because infrared divergences here appeared, but again, we kind of postulate similar to that was done for the spin chain, XZ spin chain by Jim Miwa and the collaborators, that these operators satisfy this type of conditions. It's the analog of the so-called first type of vertex operators in the latest systems. Satisfy the relation with the certain R matrices, right? And you see that it's different because this R matrix involves two R matrices from left and right hand side. Now we have the algebra Young-Boxer type algebra. But to say this type of algebra is called the Molochikov-Fadeev algebra. But anyway, what's important that this matrix should impose certain conditions, particular for self-consistency required unitarity of this matrix, associativity and Baxter relations, the crossing of this relation. Crossing required appeared from the additional bilinear relation for the just operators. But what's important here that there is no difference, no reason to expect that this matrix has a different properties, right? Because now it depends on two-dimensional variables and there's no any difference. But however, we still can satisfy all these requirements by assuming that a matrix has a form of just the usual six-vertex symmetry by certain interizing factors, which now it doesn't, not a function of ratio. And the conditions, the unitarity require these conditions and crossing that one. And also, also the symmetries with some additional requirements. And you can actually do the perturbation and check that indeed the just operator satisfy this condition in weak coupling expansions. And this is a form of these factors, interizing factor, how it depends on magnetic moment and the perturbation theories. Okay, and so the equations now. So before we proceed further, to write the functional equations for the fidelities, we need to know what is exactly what are these factors. What is the interizing factor? It's most important ingredient in the functional equations. And the idea now, you can, here is the proposal for this factor. We can check on the first order perturbation theory that the matrix satisfies these conditions very simply. If you differentiate with respect to the, this is more or less kind of Conda scale, Dirichlet derivative of Conda scale alpha, right? So you get some simple expressions, very simple expressions, and it's satisfied in the first order. If you accept that this is true for any order, then this is a predictions. So how this factor will look like. You can immediately solve these equations and construct this one. We can do some, not direct, but some check of these relations. But so this is actually a kind of proposal. And but after, if we take this, we accept this, then we can check that all necessary conditions satisfied, unitarity and crossing and whatever, and the perturbability also perturb the value what happened in the second order perturbation theory, which was never was done on the first order. But principle the can be checked in the perturbation theory, and this is a prediction for the second order perturbation theory. It's like a matrix. It's population of solitonous matrices. Okay, and so in general, they don't have solutions except on the once you have a prediction for the interizing factor, then you can write a system of functional equations like a four-factor bootstrap, very similar to four-factor equations, and actually solve it with a certain reasonable analytical assumption, solve this equation, make a prediction for the fidelities, and this is at the moment the whole result exists on the predicting stage H1 equal H2 equal to 0, and here the prediction for the fidelity alpha. Alpha here is remember this is logarithm of E1. It's upon the scale T on the 1, T on the so it is, you have systems on the system with one temperature with one temperature, another temperature, no magnetic field, and that is a formula for when overlap of the vacuum state. In this case, the magnetization equal to 0, so D12 is equal to 0. So in other words, omega 1, omega 2, actually it's a constant. It's constant. It doesn't depend on L. It has a finite limit. So this is a result. And this some numeric was done for this, and this is some result of extrapolations, and this is a prediction from just plot these functions. Plot these functions, and you see that it matches quite well. It's difficult, numerically it's quite difficult. Okay, so I'm going to finish this.
Questions?
After class?
So that just the last comment I would like to make. There's some interesting the relation for the for these functions, right? Which probably the most important result of this conjecture. This equation can be written actually once you slightly modify the definitions of amplitude R to introduce these factors. Then you see the relations. This derivative. It's kind of overall dilations, right? We change the overall scale. Alpha and beta. It's alpha logarithm E1, beta is more or less logarithm E2 on the temperatures on the one over the range. So these operations, it's dilations, overall dilations, and you see that derivative is very simply related to the orthogonality exponent. It's kind of much. You see the formula, which is I don't know if it's indeed correct. It should be explained very simply. So relation between the interesting factors and the orthogonality exponent. All right.
I guess in the sort of theory of the Kondo effect in fermion systems, as this Fermi liquid picture
Yes.
would tell us how we expect the phase shifts to depend on
Yes.
field on. And I'm
Well, the
wondering-
first shift, the exponent actually, the exponent d, it's a more or less it's a difference of the first shift. Right, it's a d.
Yeah.
Well, the d it's but we are talking about the next subleading terms of the symptom, the fidelities, which is much more complicated. But you see that the submatrix, you see that expressed in terms of the shift. It's a period condition, but it's kind of unusual. It's not, you see, logarithms are not equal to d because this is plus and this is minus. Right? And naively, you can say, oh, okay, so it should be c shift. Or it's a difference of values, but it's not true. So that it's much more, well, it's clearly expressed in terms of magnetic moment. It's unlockable way.
In inverse scattering, so Joss function, all the technology you are using, finite density can also be get if you go in finite volume. You have a finite density of excitation, and eventually you bring L to infinity. However, as far as I know, the treatment that is done is different if you take infinite volume with this boundary condition, or on the other hand, you impose quantized condition on a circle. Are they equivalent or they produce different results?
You mean result for what?
I mean,
For
you
the
have-
for the kind of specific work.
No, I mean, you have all the technology of Joss function, transfer matrix, all this stuff.
You see, the Joss functions, I don't know, the Joss function doesn't exist for. Yeah, so this is the Joss function particular useful in the case of infinite systems.
But what about if I quantize different? I put periodic, I take finite density, and then take the limit. Do I get the same result or not?
I don't know, but you probably, as far as I understand, you're talking, you want to consider this as the channel when the actually the space is infinite, right? This channel. I'm doing the channel when the space is infinite. Now you can do this in infinite, but now consider the boundary state for.
But in the other direction, instead of infinite, take finite.
But but infinite can be obtained from the finite, right? You start with the finite, pose the periodic boundary condition, then send it. But I don't know. Frankly, speaking, I don't know how to do this.
I'm asking the expert because
No,
if you read the book
I
of,
don't know.
no, but if you read the book of Fidelities, Dr. Jan, it's completely unclear at this point.
That's still this. Probably for me, it's more. How to how to do this using the starting with the, let's say, periodic boundary conditions, doing combining, and then sending the. Well, you certainly see that in this case, right? It's very difficult to proceed with the limit, you know, rigorously describe this limit, but at least you can guess. This is in the spirit. This is very similar, as I already said. It's very similar to the vertex operators algebra approach for the magnet, XSF magnet, with the disorder in the disorder regime where there is no gap. As far as I understand, the algebraic structures, rigorous mathematical structure behind this is very unclear, because in the gap regime, let's say delta less than -1, you have a picture with the quantum affine algebras and everything more or less mathematically okay. But in the regime when they have a gap, the problem of the limit is because of massless excitation. No, they did not how to formulate it, how to consider the system with the infinite number of sides. That's I find this in the physical reason. So you see the idea is just to postulate the relations and try to solve and check them.
For questions?
I have a kind of technical question. So this your elaborator from your papers with Bajanov and Zamolodchikov. So field phi was quasi-periodic.
It doesn't matter because we are doing here. Here actually I'm starting with the segment x to v1 to y2, right? And the only relations I need to use here, I use only this one. That is epsilon y1 minus y2. Right? I cannot. This is this point. But because in that point we're interested in the monodrome, we're interested in the trace of it, right? So we impose the boundary. But here I'm just doing not a transfer matrix, I'm doing the monodromy matrix. And the monodromy matrix has 4 elements, right? And when I send the y, this goes to minus infinity, actually this column doesn't have a limit, but this one can be. I'm talking about the only part of it. Not, and that time we take the traces. But here, and it was on the finite limit, we impose the periodic boundary condition, take the trace. But here it's slightly different. And this is in the spirit the classical systems with the periodic boundary conditions, or phase decaying, or finite density boundary conditions. In principle, the inverse scattering method developed different. Everything comes from the monodromy matrix, but you should focus for different elements.
Actually, I believe you can check also your results from strong coupling limit in terms of G, because then you can treat sigma 1 as kind of perturbation. You can diagonalize a part of your problem.
For G, so G equal the G restricted from 0 to 1. G equal 1. It's a isotropic quantum model, and then you have a fast transition to call it post-restored.
I mean, if you formulate it in terms of bosons, right? So then you have this, let's say, sigma 3 part, but also you have this sigma 1 part, right?
Yes.
Right.
Yes, sigma 3, right? Yeah. And you want to do the perturbation in terms of
sigma
J,
1, yes.
Of J, right?
J, yes. Because so imagine
yes, that's a point. That's I call a conformal perturbation. Yes, it's possible to do, and for example, check the orthogonality exponent, and you can do this. Yes, this can be done. This can be done, expansion, and actually check the orthogonality exponent. in terms of expansion, not in terms of exactly in G, but in perturbative.
Yeah, it's perturbative.
Yeah, it's possible. I call this person conformal perturbation.
Thank you.